Now, in today's lecture, we are going to talk about critical points and inverse mapping. So, in our past lecture, we saw that we could do this conformal mapping thing if at certain point the derivative of the mapping f of z naught, that means a particular point, is not equals to 0, right? This was the previous criteria. However, today we want to relax this condition. By this I mean that we are saying that if we have some analytic function in a domain or some mapping that is given by f of z from z to w plane, and this is also non-constant in our domain, and we are also supposing that we can have for any z naught belongs to D, that is for any particular point z naught which belongs to D, assume that f of z naught, that is the first derivative f prime of z naught, this can be 0. In fact, the second derivative can also be 0, and so on. We can go up to, let's say, n minus 1th derivative. All of these are equals to 0, and the first non-derivatives the first non-zero derivative will appear at f of n z naught, which this is non-zero. So this is the condition that we are working with today. So what happens when you try to map something from the z to w plane and you have this in your pocket? That means the derivatives up to n minus 1, the order n minus 1 derivative, they all are 0. So we want to show that under this mapping, under this w equals to f of z, that means the mapping where z goes to f of z, this mapping will magnify the angle between two intersecting differentiable arcs that meet at z naught n times. This mapping will magnify the angle between two curves intersecting at a point z naught by n times. So that means that on the z plane, this is the picture on the z plane. If this is two differentiable arcs and this is the angle theta, then under these conditions on the w plane u and v, this angle theta prime will be related with the angle theta as theta prime equals to n times theta. So how do we prove it? So this will be the proof. So to prove it, let's draw a picture first on the z plane. Again, this is x and y. Let's say this is one of the curves, this is the other curve, this is the intersection point z0, and let's take a point as z2 that is near z naught, and this is another point z1. But the condition we are assuming for the simplicity of the proof is that the distance of these 2 points from z naught is equal. You can also do it by saying, okay, they are not equal. I want to take distances as r1 and r2. You can also do that, but for simplicity we are assuming that modulus of z0 minus z2 equals to modulus of z0 minus z1. This is denoted as r. This is for simplicity. Okay, now we want to investigate what happens to this angle theta 2 minus theta 1. Why theta 2 minus theta 1? Well, you can see that this is, let's say, theta 2, and even though this drawing is not very good, let's call this theta 1. The arguments of these two differentiable arcs, we want to see what happens to this, so let's call it theta. Okay, now what we can do is that we can do a polar representations of these distances. That means we can write z naught, sorry, not z naught, it should be z1 minus z naught equals to r e to the power I theta 1, and similarly z2 minus z naught equals to r e to the power I theta 2. If you divide these two, you will have z1 minus z naught, z2 minus z naught as e to the power I theta. That means e to the power I theta 2 minus theta 1, which we write as theta, right? So now let's try to do something interesting, is that from here you can see that the argument of this quantity z1 minus z naught, z2 minus z naught is just the theta, right? And what we want to do is that we want to take a limit where r goes to 0. That means since we're talking about differentiable arcs, these distances need to be go to 0, tends to 0 to be exact, and we want to see what happens of this argument while that really limit reaches on the z plane, and how this mapping gives us the argument on the w plane. So since we are calling theta the argument on the z plane, let's call phi as the argument on the w plane, as argument on w plane. That means how do we write it in the w plane? If you have these 2 points, then on the w plane each and every point is given by this mapping, right? Z goes to f of z. So we are having 3 points, that means z0, z1 and z2. So just like that we are defining theta like this one. We are defining phi as f of z1 minus, sorry, it should be an argument word in front, so oops, yeah, this should work. So this is just argument of f of z1 minus f of z0, f of z2 minus f of z0 or z0. Alright, now we want to take the limit. So we are calling theta as the limit when r goes to 0 of z1 minus z0, and let's say this is z2 minus z0. Oh wait, sorry, what we are doing, we are calling theta 2 minus theta 1. Oh, in that case there should be a minus, so we need to reverse this, sorry about that. So e to the power I theta would be z2 minus z0, this is z1 minus z0, it would be the inverse. So 2 will become 1 over here. Similarly over here theta phi would be z2, z0, and this there will be a 1. So these are pretty small corrections. You can also do it the other ways. All you will have is that you will have an extra minus in front. So now after taking this limit, we are calling this as theta. Similarly on the w plane, phi would be defined as this limit where the distance on the w plane will also go to 0. You can use r prime if you want, and this would be given by argument of f of z2 minus f of z0 divided by f of z1 minus f of z0. And since we are telling you that the distance, that means the r will go to 0, so it's better to keep just only 1 r so that we can avoid confusion for now. Now we are going to use this quantity and manipulate it. So we write phi as limit r goes to 0, argument of this whole thing, but not what we're going to do is that we're going to divide it on the both side, z0 by z2 minus z0 to the power n. Remember that we have assumed the derivatives up to n minus 1th order will be 0. and the first non-zero derivative will come in the order of n. So that's why we are doing this trick over here, that is the division trick. And here what we're going to do is that we're going to write f of z1, f of z0, and we have this z1 minus z0 to the power n. Close this whole thing, but since we have divided it, we have to multiply these things as well. And if you multiply them, this will be just z2 minus z0 to the power n and z1 minus z0 to the power n, like this. Okay, in the next line what you're going to do is that if you realize that this function f of z, you can do a Taylor expansion for it around that point, the point of interest, let's say z0. It can be written as f of z0, f prime of z0, f double prime of z0, sorry, it should be a z minus z0 over here, and z minus z0 by whole square. There should be 2 factorial and so on. Then these terms over here, these terms would actually give rise to the nth derivative, right? So what I'm meaning is that this limit r goes to 0, f of z2 minus f of z0 divided by z2 minus z0 to the power n would actually give you the nth order derivative at point z0 divided by the n factorial. This is what I'm saying, alright? Because if you just look at these terms over here, you can easily see that, and you have to compare this with the Taylor expansion thing. So if this is the case, then we can finally write phi as limit of r goes to 0, and we can write it as the argument. Obviously this is an argument, so we can write it as the argument of this guy all over the place. That means the argument of z2 minus z0 divided by z1 minus z0 to the power n. But what was this thing? This thing was nothing but theta itself. That means the argument itself was theta, alright, and all the arguments of this guy were written in terms of the exponentials. So this would simply give us theta phi is equals to n times theta, alright. So this tells us that if we have some critical points, why am I calling it a critical point? Because at that point of interest, f of z prime, this is this can be equals to 0, and this is where conformal transformation ceases to exist. So that's why we needed this whole critical point thing, and this is more of a inverse mapping thing, alright. So this will be it for today, and before I finish off, one example, a short example would be that let's say you have a triangle on the xy plane, that means the z plane to be exact, and let's say this is the angle pi by 2 written by b. Here you have an angle a which is given by, let's say, pi by 4. Here you will have another angle which is given by pi by 4, and let's call it c. This line is given by x plus y equals to 1, y axis will be given by x equals to 0, and x axis will be given by y equals to 0. If you map this triangle using a mapping that is denoted by w is equals to z squared, you will immediately see that this w equals to z squared implies that u is equals to x square minus y square and v is equals to 2xy. This is very easy to see. And now if you eliminate x and y's and write u in terms of v, this will become v equals to 1/2 times 1 minus u square. So you have to use these lines, that is the lines which bound this triangle or make this triangle, and if you apply them over here, this will give you this kind of transformation, and the picture will look on the UV plane is something like this. So you will have an arc type of thing. Here these angles will get preserved. However, so this is our A prime, which is correspond to A. This is, let's say, C prime, which correspond to C. But this angle pi by 2, it would not be conserved. Rather, it would get multiplied with 2, and this will become pi. So this is how this critical point method works, and this will be it for today. Thank you.